All right, let's go ahead and get started. I want to welcome you back to this fifth screencast of Unit 5. This is chemical bonding, and we've been talking about Lewis structures for molecules. In fact, we left last time with hydrogen cyanide, and we're going to be looking for the Lewis structure for HCN, or hydrogen cyanide. So they're telling me it contains one hydrogen atom, one carbon atom, and one nitrogen atom. Let's draw those in. First of all, hydrogen is going to have one valence electron, just like that. It's in the first column. Carbon is going to have 4. 1, 2, 3, 4. Remember not to pair up until you have to. And then nitrogen is going to have 5. We'll put 2 there, 1 there, 1 there, and 1 there, just like that. Now let's add up valence electrons. We've got 1 for the hydrogen, 4 for the carbon, and 5 for the nitrogen, for a total of 10 electrons, just like that. Now let's draw the basic skeleton structure. Remember that carbon will be in the middle, right? Carbon is going to be in the middle. So we'll put that one right there. We'll put the hydrogen here, and we'll put the nitrogen here, just like that. So let me begin by taking some of these electrons, some of these 10 electrons, and forming what we call the skeleton structure, just like that. So I have to connect the hydrogen, the carbon, and the nitrogen with electrons. So that leaves 6 left. I've used 4 of the 10. I've got 6 left. So I'm going to put those in. So 2 here, that's 4, and that's 6, and that's it. That's a total of 10. 2, 4, 6, 8, 10 electrons. Well, guess what, folks? The nitrogen doesn't have enough electrons. So what did I tell you that was going to happen if you don't have enough electrons? What do then? You try a double bond, right? You try a double bond. So let's do that. Let's try a double bond. So we're going to have the same skeleton structure, just like that, H, and then C, and then N. Can't put a double bond there because hydrogen can only have 2 electrons. Let me try the double bond right there. Now, just by connecting the atoms together, I've used 6 of the 10 electrons. Where do I put the other 4? Well, I'll put 2 here, and I'll put, say, 2 there. That's a total of 10 electrons. But does every atom have the requisite number, or the correct number of electrons? Well, the hydrogen certainly does. It has 2 electrons right there. The carbon, let's see, 2 here, 2 more there. That's 4, 6, 8. Carbon looks good, but what about nitrogen? Nitrogen has only 2, 4, 6 electrons. So that structure is not going to work either. So what if you try the double bond and you still don't have enough electrons? In that case, what's going to happen is you're going to have to try a triple bond. So let's try a triple bond just like that. So there's 6 electrons right there. And then I'll put 2 more just like that. That's 8 electrons. Where do I put the other 2? Let me put them right here. Let's try the hydrogen first. Hydrogen has 2 electrons. It's supposed to have 2 electrons. Carbon feels as though it has 2, 4, 6, 8 electrons. Carbon looks good. Nitrogen, 2, 4, 6, 8 electrons for the nitrogen. This looks like a reasonable structure. There's just one more thing I'm going to do, though, and that is I'm going to replace these bonded electrons with little dashes. So I'm going to say H here, a C just like that, and then triple bonded to N, and a double bond or a triple bond just like that, and then 2 more electrons. And that's it. That is my structure for hydrogen cyanide. Okay? It meets all the requirements for a good structure. What I want to do now is I want to turn my attention to what we call molecular geometry. So we've talked a lot about how electrons are arranged around atoms and how many electrons that atoms should have. But what we want to do now is we want to look at the 3-dimensional structure. What a molecule might look like in space. 3-dimensional space, okay? So we're going to need our imagination just a little bit here. We're going to use something called valence shell electron pair repulsion theory, okay? Valence shell electron pair repulsion theory, or VSEPR. It's used to determine the geometry of molecules in 3-dimensional space, okay? By the way, folks, if you really want to impress your parents, when they ask you what you studied in chemistry, tell them, well, we were talking about valence shell electron pair repulsion theory, and they will really be impressed with you, okay? So VSEPR, don't forget it. So VSEPR theory states that electron densities is going to try to get as far away from each other as possible. And we use this idea to help us to understand the geometry of molecules, okay? Remember that electrons are negatively charged. They're all negatively charged. So electrons then are going to try to get as far away from each other as they possibly can, all right? So what we want to do in our study of molecular geometry is we want to start with the simplest geometry. We want to start simple and then gradually get more and more and more complex. Well, as it turns out, the simplest molecular structures are what we call linear molecules. Any 2 points are connected by a straight line, all right? And sometimes 3 points can be connected by a straight line, as we'll see with this particular structure here. So these include examples of these are H2, Cl2, HBr, and CO2. Let's talk a little bit about how H2 and Cl2 would be linear. So you can imagine 2 points. These are the nuclei. The hydrogen here and the hydrogen here are the nuclei of the hydrogen molecule. I'll just connect them with a straight line that I'll use a dash to do. That's a straight line, right? So we call that a linear molecule. Any diatomic molecule, no matter how I draw it, is going to be linear. If I have HBr, I still have 2 atoms, and they're going to be connected by a straight line like that, so we're going to call that linear as well. So all those are linear. Now, what about CO2? What about carbon dioxide? Well, for carbon dioxide, we've got 3 atoms. But as it turns out, those 3 atoms, I'll put a carbon right there, an oxygen here, an oxygen right there. As it turns out, there's a double bond here and a double bond here. We won't worry about that just yet. But the point is that these electron densities, the electron density on the left and the electron density that you see on the right, are going to try to push as far away from each other as possible. Again, we call that valence shell electron pair repulsion theory. So if this electron pair or this electron density pushes this way and this electron density pushes in the opposite direction, you can see that that is going to form a straight line, and we call this a linear molecule. So once again, anytime that you see a molecule that has only 2 atoms in it, like HH or ClCl or HBr, we have a linear molecule. But sometimes when you have 3 atoms, you can have a linear molecule as well. Now, it doesn't happen every time, but it's certainly a good possibility that if you have 3 atoms, that there's going to be it's going to be a linear molecule. And we'll talk about what would make a molecule have 3 atoms and not be linear. In fact, we'll do that right now. Let's talk a little bit about what we call bent molecules. So bent molecules have the shape that appears bent, right? Obviously, for obvious reasons. They appear bent. Now, lone pairs of electrons cause molecules to bend. An example is H2O. So this would be a bent molecule for obvious reasons. It doesn't form a straight line. It's bent. But once again, what causes it to bend? Well, the Lewis structure for water, for example, so water would be an example of an atom, or a molecule, I should say, that is bent. And the Lewis structure is going to be this right here. We're going to have 2 lone pair of electrons here. They're not bonded to anything, and 2 here. But here's what you should know, that these pairs of non-bonded electrons, these pairs of electrons that are not bonded to anything, are influencing the geometry. This pair of electrons and this pair of electrons are causing the molecule to be bent down so that this electron density is pushed this way, that electron density pushed that way, and we have what we call, again, a bent molecule. Now, when somebody says the bent molecule, I want you to think of the prototype. The most important molecule that has a bent shape is going to be water. Think of water, okay? When I say bent, I want you to think of water as an example of a bent molecule. CO2 would be an example of a linear molecule. Let's move on. Remember, we're going from simple to more complex. Trigonal planar molecules. Well, what does trigonal mean? Trigonal means three, right? Tri means three. Planar means everything's in the same plane, right? Everything is in the same plane. So trigonal planar molecules have one thing in the middle and three things that are extending out from that center, right? Three things that are moving out from that center. So we might have, for example, boron trifluoride. So we have boron in the center, so this central atom is a boron. We have a fluorine, and a fluorine. Now you may say, hey, wait a minute. Boron does not have 8 electrons around it. You're right. There are a few exceptions to the octet rule, and boron is an exception. It is one of those exceptions to the octet rule. By the way, you already knew that hydrogen was an exception to the octet rule. It requires only 2 electrons. But boron sometimes only requires 6 electrons, and this is one of those cases. But the point is we have a boron in the middle, boron atom in the center. We have fluorine, 3 fluorines surrounding the boron, okay? And those fluorines are going to move out to the vertices of think of a triangle in a plane. Think of this sheet as a plane. By the way, if that were true, what would this angle be? Let's think about that for just a little while. What would that angle be? Well, in fact, what would all those angles be? They'd be 120 degrees, okay? They'd be 120 degrees. So, the point is this. Trigonal planar molecules are trigonal because there are 3 things extending from the center, and they are planar because everything is in the same plane, right? Everything is in the same plane. Does that make sense to everybody? Okay. Let's move on. We've talked about, let's kind of review a little bit here. We've talked about linear molecules. That was the simplest type of molecule. An example might have been CO2 or any diatomic molecule like H2 or Br2 or HBr, anything like that is going to be linear. Then we talked about the bent molecule. The bent molecule prototype was water. Now we're talking about trigonal planar molecules like BF3. Let's move on. Another important molecular geometry would be this one right here. Tetrahedral molecules. What does tetra mean? What does tetra mean? It means 4. So we have one thing in the middle and we have 4 things surrounding it. We have 1 atom in the center and 4 atoms around it. An example might be CH4. So we have carbon right here, just like that. We have a hydrogen here, a hydrogen here, a hydrogen here, and a hydrogen just like that. Folks, this bond angle right here is 109.5 degrees. You don't have to remember that, but I'm just so you know that angle is 109.5 degrees. But the point is this. A tetrahedral arrangement is one in which all the bond angles are the same, and it doesn't matter which way you turn it. So that's what we mean by tetrahedral. One more time, methane, or CH4, is an example of a tetrahedral arrangement. Okay? Well, we've gone through a couple of the more simple geometries. We'll take a look at some more difficult ones in a few minutes, or probably on the next video. But for right now, I think it's a good place for us to kind of practice what we've learned and just kind of solidify our understanding of molecular geometry to this point. So here we go. What is the geometry of HBr? Is it linear, bent, trigonal, planar, or tetrahedral? Well, for HBr, there's only 2 atoms. It's hydrogen and bromine. And what did I tell you about what happens when you have 2 and only 2 atoms? You connect them with a straight line. This one's going to be linear, right? It's going to be linear. What is the geometry of CCl4? Well, carbon tetrachloride, as this is called, has a carbon in the middle, right? Let me draw that right here as best I can. Okay, it's hard to draw a 3-dimensional structure in a 2-dimensional space, but Cl right there, and then kind of out this way, I'll draw that little kind of wedge there, is to try to bring this structure. Let me do a little bit better job of that. And I'm trying to pull this out just a little bit further, just like that. And then we'll put another Cl here, another Cl right there, just like that. And that would be tetrahedral. Folks, I'll see you on the next one. Bye-bye.